graphene known with its superlatives like thinnest, the strongest, the most stretchable, the highest thermal conductivity, and highest electrical conductivity. And however, graphene has some handicaps like high sheet resistance and missing band gap. To get rid of or to get over these kind of handicaps, we have two approaches so far in the literature. One is the multi-layer graphene synthesis, and the second one is chemical doping. The multi-layer graphene, yes, is easier to fabricate or to obtain, but however, as you get thicker, you get a rather graphite structure rather than graphene. So the chemical doping is much preferable. But let me emphasize, when we talk about the chemical doping, we would like to have graphene in the structure of the graphene, in the carbon structure, or replacing carbon by impurities like boron or nitrogen. But in our case, when we, with the idea using boron-doped graphene, we would like to see their effect on the silicon-based solar cell. I mean, we want to use them as a transparent conductive electrode. So let me compare before we go through what we did. Single layer graphene sheet resistance is about 600 ohm per square and transparency is 97%. But however, it's rival ITO with 80 nanometer, which is commonly used in transparent conductive electrode, sheet resistance 40 ohm per square and transparency 85. We are okay with the transparency, but the sheet resistance of the graphene must be reduced to be used as a transparent conductive electrode. In general agreement to be used graphene or any materials as a transparent conductive electrode, sheet resistance should be around 100 ohm per square and transparency over the 85%. So what we did in our case, we grow graphene in CVD system. We have a CVD system with 3 zone attached with 6 MFC, and we are able to control the 3 different furnace zone with different temperatures. And we use methane as a carbon source. So we grow all the graphene on the copper foil. And of course, is the general or synthesis process where we did heating, annealing, and growth cooling processes. And in the characterization side, we use mainly Raman spectroscopy, which is much easier for us, and straightforward method, and easy to handle the sample during the measurement as well. And we can use the sample afterwards as well. And of course, we played with annealing time, with the growth time, but how we check the Raman to make sure that our graphene is homogeneous and single layer. We check the 2D and G peaks as you see in the screen as well, and their position, their intensity, and the ratio in between, and they are full with half maximum. Here's what we did so far for the pristine graphene. But in this talk, I'm going to talk about the graphene doping, and we choose boron and nitrogen mainly for doping. But in this special talk is going to be, going to talk about the boron doping. Why we choose doping to study boron rather than nitrogen. Nitrogen is very well studied in the literature. So boron side is a bit weak. We try to get the boron side or to get a bit more literature about the boron. But let me go back why boron or why nitrogen used in the doping process, because carbon, their atomic ratio or radius is close to carbon 1, and the idea to do doping to make the carbon or in the graphene structure substitutional doping in the carbon structure. I mean, rather than using other type of metals to do doping, we want to make sure that the graphene is stably doped and substitutionally doped using boron or nitrogen. Of course, we know Fermi energy in the Dirac point in the pristine graphene, and by doping like boron and nitrogen, we try to move the Fermi energy. In our case, when we try to dope the graphene with using boron, we use 3 different sources like diborane, 3-ethylborane, phenylboronic acid. The first one, diborane, is in a gas form and is very well suitable to be used in the CVD form, CVD furnaces. And let me emphasize here, diborane is only boron source for us. We use methane for the carbon source. However, for triethyl boron and penyl boronic acid, as you see in their chemical formula, we use them both as a carbon and boron source. I mean, we didn't use any supplementary or additional carbon source during the synthesis of both. Let me move to diborane doped graphene. Initially, we try to follow the synthesis procedure with the flow by changing the diborane flow rate. So we try to do 10, 20, 30 SSEM. Then we try to align or adjust the growth time. And during this, our initial characterization was Raman spectroscopy as well. As you see, as we increase the flow of the diborane, the graphene structure, we lose the graphene structure in terms of homogeneity and in terms of the thickness. Particularly 30 SSEM or 40 SSEM provided us with the graphite structure. I mean, very thick structure. However, we were much happier with the 10 SSEM diborane flow to be able to obtain single or double layer graphene. And these measurements were supported with optical measurement in particularly for 10 SSEM diborane, where the optical transmission was 94%. We moved, as I mentioned, we moved after we adjust or decide or optimize the flow rate, we try to align or adjust the growth time as well. We try to do 20, 30, 40, even 50 minutes growth time, and we decide based on Raman spectroscopy results, 30-minute growth time is the best for us in terms of quality. I mean homogeneity and the thickness. But yes, we agree that we have something in the structure, but to make sure graphene doped substitutionally with boron, we need to check, or we have checked XPS measurements, X-rays photoelectron spectroscopy. So we look at the B1 and C1 spectra, I mean boron and carbon spectra, and the boron side. Let me talk about the boron side. As you see here, the 191 electron volt peak is the main boron peak, and more importantly, 187 peak is the substitutional boron peak, which make us, or we make sure that the boron is substitute carbon in the structure. And in this case, when we use 10 SSEM diborane, the boron content in the graphene structure was 2.4. And the thickness, we measure thickness using AFM, and we were able to see around 1.5 nanometer thickness, and which is related to the 1 or 2 layer. The other source, we were triethyl borane, and triethyl borane, as I said, is used as a carbon and boron size together. I mean, this is in the liquid form, and we try to adjust the molarity with using hexane. We start with 0.5 molarity tab, 1 molar and 1.5 molar. And for the comparison in terms of Raman spectroscopy, we add pristine graphene Raman spectra here as well. And we were much happier to see 0.5 molar tab is much homogeneous and much thinner than the other films, and much closer in terms of spectra to the pristine one. And again, after that, we try to align or we adjust the growth time, and then we decide, especially if we check here, the 10-minute growth time was the best for us. In particular, I didn't show you before, but let me emphasize here, the D peak was related to the defects. Yes, we know the impurities can introduce defects, but more importantly, a shoulder of the G peak, which we call it D prime. D prime is associated with the foreign atoms in the structure. So we see that in the Raman spectra, but to make sure these foreign atoms were boron, we further proceed with the XPS, X-ray photoelectron spectroscopy, to see the boron peaks, whether it is substitutional or just addition or on the edge or which type. In our case, when we use 0.5 molarity when we grow graphene with 0.5 molarity TAP or triethyl boron, we find out 8% boron in the structure. But another important things to emphasize here, the most homogeneous and the most boron content of graphene synthesized up to now was this one. The TAP one. So again, we check the thickness of the film here, and we try to see whether it is one layer or two layer. As you see, as the thickness is around 0.8 nanometer, and this is called single layer in the literature. Yes, I know, or we are aware it's a bit thicker than the pristine one, but it is something expected, and it is concluded as a single layer, and we can discuss it if you have any question with it. And the last study was phenylboronic acid. Again, this is used both for carbon and boron source. We didn't feed the system, our CVD system, with any other gases. So we try to adjust the growth processes using 0.5 gram, 1 gram, and 1.5 gram. As I mentioned, this was in a solid form. And thanks to the 3-zone CVD system, we were able to use different zones with different temperatures and able to grow graphene with using these kind of materials in different zones. So in our case, using 0.51 or 1.5 gram, we were much happy, or we were much more satisfied in terms of homogeneity using 0.5 gram. And once we have that, again, we check the XPS before we go any AFM measurements. Again, we were happy to see the boron content and boron stability. 2% boron was found here. And again, the thickness were measured around 2 nanometer, which is a bit higher than the single layer, but we call it double layer. And what we did, yes, after we synthesized that kind of graphene, pristine graphene and boron-doped graphene, we synthesized silicon-based solar cell. As I mentioned at the beginning, our aim was to use graphene on top of silicon solar cell with the ITO structure, either to remove ITO or to use them together as a hybrid structure, as a transparent conductive electrode. So in our case, here, as you see, when I use graphene with ITO, the pristine graphene and the boron-doped graphene, we did this similar study for nitrogen-doped graphene as well. But in our case here, the pristine graphene, I hope you can follow me in here. 100 nanometer ITO silicon cell with 100 nanometer ITO gave us 10.9% efficiency. But when we use ITO along with graphene, single layer pristine graphene, the efficiency went up 12.1. And when we use ITO along with boron-doped graphene, again in single layer or double layer maximum, we obtained the efficiency 13.2, and the increase in comparison to pristine one, the increase of the efficiency of the cell, this is quite nice. This is 13% or 21%. At least in many, we prepared or we fabricate many of samples, 100 samples, solar cells, and we didn't go below 10% at all, especially for pristine. Okay, I'm about to finish here. What I talk about the graphene, pristine graphene in CVD system, a boron-doped graphene using diborane, boron-doped graphene using triethyl borane, and boron-doped graphene using phenylboronic acid. And those samples, in comparison, if we compare 3 of them, yes, diborane is easy to use in a CVD system and much easy to obtain homogeneous film, but triethyl borane and phenylboronic acid it has advantages, have advantages over deboron because we don't use any additional gas during the synthesis of them. And both pristine and boron doped graphene used in the silicon-based solar cells along with ITO as a hybrid structure, and the cell efficiency improved well. I would like to thank you for inviting me and for your attention. And would like to thank my student here who worked in this project, and Tubitak as well. And is there any question, please? Thank you very much.